Okay, well, good morning, welcome. Countdown has begun, so I'm going to start. This session is entitled Bringing the Performance of Structs to Java, sort of. Now, I must admit, I am still trying to come up with a better title for this presentation. I did try to think this morning of some witty thing that I could do with relation to Brexit, but nothing came to mind. That was just depressing. So anyway, let's move on. So quick show of hands here. Who here has either programmed in C or C++ at some point? Okay, good. So most of you are going to know what structs are. Right. Now, the idea behind this was a project that was started at Azul, the company that I work for. And it was really about looking at how to improve the performance of Java applications, because that's really what our business is. We sell JVMs, one of which is a commercial one, which we replace the garbage collector on, and we do various things to improve performance. So we're always looking at ways to do other things. And this was a project that we started, again, looking at how to improve performance of Java. And really, it's about looking at how other languages, like C and C++, take advantage of the way that memory layout can be used in order to get better performance in certain situations. And really what we wanted to do was to take this idea of how structs work in C and C++ and apply it to Java. And the key things here, and I'm going to say this several times during the presentation, is it is about speed, it is about for regular Java objects, so we don't want to do anything different in terms of Java objects, and it's about being on the heap. So these are the three key things. Speed for regular Java objects on the heap. Now, in terms of what we're not looking at, we are not looking at how to improve things from a footprint point of view. So we're not trying to reduce the amount of space that's used to store objects. We are not looking at doing things outside of the heap. So we want to continue to use the memory management system exactly as it works today, from the point of view of creating objects, from the point of view of having a garbage collector that automatically reclaims space. And we're not interested in dealing purely with immutable objects. What we're going to propose, what I'm going to talk about for the rest of this presentation, allows you to use immutable objects if you want to, but there's no requirement to do so. So if you want mutability in your objects, then they will work just as well as immutable objects, because it's for regular Java objects. Now, if we look at the goals of this project, there is some relationship with other projects, and people often ask about this when I talk about this type of thing. And the relationship is to various other things. So value types is something that has been proposed for JDK 10. And value types is about allowing you to do things like having generics for primitive types, so that you don't have to encapsulate a primitive in an object in order to put it in a collection. You can just use a primitive as a value type. Value types is about being able to return a tuple, more than one value from a method. So these things are not the same as the goals that we have for object layout. Similarly, there's a project which has been started around packed objects, about how you can compress more data into the same space, how you can put information in different ways. And this kind of relates to a replacement for JNI. It relates to the idea of a foreign function interface. And so again, from a goals point of view, we're not trying to address the same thing as packed objects. Object layout is focused on speed for regular Java objects on the heap. There is some overlap in terms of how things might work. And you can think of it in the same way that in terms of collections, you can have an array list, you can have a hash map. Now, they're both collections, they're both ways of storing objects as a collection, but how they work is very different underneath. So that's the kind of overlap that we're looking at there. And what we can do is we can create a nice Venn diagram which shows these three different types of project and look at the different aspects of those and how they do overlap in terms of their use. So first of all, we've got value types. Now, value types are very much about immutability. So a value is a value. You can't change it. So it is immutable. It's about return values, as I said. So the idea of being able to return a tuple rather than a single value. It's about having things on the heap, but it's also about having things on the stack. So there's some differences there. In order to use value types, you are going to need new code. Code will be different in order to use value types. If we look at packed objects and the foreign function interface, this is about interacting with native code. So the way that's going to work is by using memory which is allocated outside of the heap. So not on the heap as we're doing with ObjectLayout. It's much more about sharing data between native code and Java code. And it's very much about precise layout of data. An example of that would be if you're dealing with a network card and you want to get access to the TCP packets that are coming through from that card, then you need a very precise layout, which is the format of that TCP packet. So that has to stay the same in terms of the memory layout. Again, in terms of using packed objects and a foreign function interface, this will require new code. You need to change your code in order to use that. Object layout. Object layout is about speed for regular Java objects on the heap. So those are the differences. And the important thing about that is that all of the objects that you have at the moment are reusable by existing code. So what we can do is we can use this without having to modify a lot of the code that we're using. Now, there are a few things that you will need to do differently because we're introducing some new classes, but that's really the level that we're talking about. It's not actually changing syntax, it's not changing structure as such. And we can see that there's an intersection between all three of these, where we might have a situation where you've got an array of small footprint values, because you can store values in the object layout just as you could any other object. So there is this very small overlap where you might find you could use all three of them at the same time. Now, in terms of the origins of this project, this really came about because of a simple argument that was being had by Gil Tene, who's our CTO, and some other people who were talking about performance in Java. And the idea was that they said, we need structs. We need structs in Java because they allow you to take advantage of the memory layout, and they allow you to take advantage of that to improve performance by using different caching, by using the ability to read ahead and do things like that. Often people try to emulate structs in Java. There have been various projects that have tried this already, and they tend to go down the route of using the wonderfully named sun, misc, unsafe in order to get down into a low level to manipulate memory at the sort of direct level. But that's not really what you want to do. And if you think about it, C and C++, most people here have already used C and C++, they get that for free because you can create a struct in C. I'm going to stop saying C++, just assume that when I say C, I mean C or C++. If you create a struct in C, it's there. You can use it. There's nothing complicated about it. It's just available for free. But then the flip side of that, in terms of Java, is, well, we already have structs. We just call them objects. Because if you think about it, struct is just a way of putting together different pieces of data, potentially different types, different primitive values, and treating them as a single entity. So an object is exactly what we do in Java to do that. It's encapsulation of data. But an object, obviously, is a little bit more complex than that because it also has behavior as well as state. What we want to do is to enable us to take the idea of a struct and use it in the same way in Java so that we can get that memory addressing advantage in terms of speed. The question then is, where does this speed come from? How is it that a struct works so much better than an object, given that the basic idea is roughly the same? What's the improvement in performance that you get from a struct? And there's essentially two different things that you can take advantage of from the low-level machine architecture point of view. One is dead reckoning, and the other is streaming for arrays of structs. What do we mean by that? Well, let's have a look at how we group data in C. We can create a struct, a square, and we simply define the struct square, and we say it's going to have 3 values inside it. It's going to have int x, int y, which is the position of a corner, and it's going to have a size, which is also an int. And then we can create one of those, and we can push it onto the stack, and then we've got access to it. If we look at that struct in terms of its layout within memory, what we're going to see is this. We're going to have, on our stack, 3 integer values, all one on top of the other, all next to each other, contiguous in memory. Int x, int y, int size. And as a struct, we essentially treat those 3 integers as a single thing. Great. OK. Now, we might want to create an array of these. So we can do that in C, where we actually have to explicitly allocate the memory in order to store those things. So what we'll do here is we'll use malloc, we'll use the size of our struct, and we'll say that we want to have 5 elements in our array. So we allocate enough space for that. We get an explicit pointer to that area in memory. And then we can store our structs in there, and we can do some interesting things with that. We can put values in there. If we want to retrieve a specific value from that, we can do it very easily. Because let's say I want to get to the 4th element in my array, and I want the y value associated with that. So the first thing is I have to remember that I'm a computer rather than a human, so I start counting from 0. So the index is actually 3 rather than 4. Well, unless you're a Pascal programmer, and then it would be 4. But in this case, it's index 3, which gives us the 4th element. So what we want to do is calculate the address of that. And we can do that simply by saying, well, we know the address of the start of our area of memory, where we stored our array. We can then increment that by 3 times the size of the structure in order to get to the beginning of the 4th element in the array. And then in order to find the value of y, we need the address of that, which is to add the size of int. So that's to move past the x value to get to the y value. The key thing about that is there's no indirection involved. There's no retrieving a pointer to get to another value in the memory. All we're doing is making a simple calculation based on the initial value and then figuring out where those things are. So that's very quick because we can simply do that as a calculation and we can get an advantage in terms of speed. So that's dead reckoning. The second thing is the idea of streaming in arrays. Again, we've got our array of square structs, and if we want to read each of those sequentially, what we do is we say, okay, give me the value of the first one, which is the struct at the pointer SQ, and then when we want to get to the next one, obviously we can use dead reckoning to get to that address, so we simply add the size of struct square. To get to the next one, we add 2 times the size of the struct square, 3 times the size of struct square, and 4 times the size of struct square. Nothing very clever about that, but the underlying hardware will then notice this. And so what it's going to do is it's going to say, you're actually referencing these areas in memory at a fixed distance, and you're doing it repeatedly. So the hardware will then start doing prefetching. Hardware is smart enough to say, right, because you're doing that, I'll start to load data from memory based on your pattern of usage to make that data available so that when you get to the next one, it's already in the cache. So this is the kind of thing that can give you, again, a big improvement in terms of performance for data access. That's the way it works in C. How do we do the same thing in Java? Well, let's look at our square, and this time we're going to create a class called square. So it's very similar. We've got class square, and we're going to have 3 integers in there, int x, int y, int size. Looks very similar in terms of our definition of it. But in terms of creating one, we actually have to instantiate that. So we get the JVM to allocate the memory in the heap for us, and we don't get an explicit pointer. We get an implicit pointer to that area of memory so that we can reference it. And if we look at what's stored in memory, we'll certainly see the same thing that we had before, where we got int x, int y, and int size. And they will probably be contiguous in memory within that structure or within that square because we've defined them that way. But we have an object now rather than a struct. An object has extra information about it. So there's at least things like an object header that needs to be included in that. So the box around that is a little bit bigger than our 3 integers. Okay, we can still kind of take that into account. But then we get into a more complex situation. Let's say we want to, again, allocate an array of square objects. So we do that by creating an array and saying it's of size 5, and then we go off and we allocate or instantiate new square objects, and we assign those to the elements in our array. That's all good, and if we're really lucky, we may get those square objects allocated contiguously in memory. I say if we're really lucky because if you're using standard allocator, then if you're using a single thread, you probably will get them allocated contiguously in memory. If you're using multiple threads and you're using thread local allocation blocks, then there's a chance you won't get them allocated contiguous in memory. But the key point there is we can't guarantee that. So, yeah, we'll accept that maybe it is. Problem comes when we do garbage collection. Garbage collection is going to move objects from the young generation into survivor spaces or into the old generation. So it's copying objects around. And again, there's certainly no way that we can guarantee in the way that the JVM and the garbage collector works in terms of standard objects that those things will be contiguous. They may get dotted around because we've got different threads in terms of the parallel collector, moving objects at different times and putting them in different places in the heap. So that's definitely not guaranteed. But it gets more complicated than that. Because, of course, I can come along and I can say, well, actually, I'm going to change one of those references. I need a different square. So I'm going to store a different reference to that square in my array. So then that's definitely somewhere else in the heap. And it gets more complicated than that. Because Java, being object-oriented, has the idea of inheritance. If we have a square object that we can store in that array, we can also store any subclass of square. So I can create a new type of object called filled square, which is bigger. It's got more information in it. And then I can store a reference to that quite legitimately in my square array. So again, this becomes very problematic from the point of view of trying to do the same thing that we have with structs. Can't do dead reckoning because we can't guarantee they're contiguous. We can't do striding because they're not contiguous, so we won't get the prefetching advantage from the hardware. So if we look at the semantics of structures versus objects, what we find is that C has an immutable array of exact same-size structures. So we've seen that from our description, that the structs are always the same size. We can't change them. We can change the values stored in them, but we can't actually change the structures themselves. And then in Java, what we're dealing with is kind of the opposite of that. We're dealing with a mutable array where we can change the references to be different objects of the same base type objects. So we've seen that we can change the type to a subtype, which could potentially be bigger than the one that we're dealing with. So the idea of object layout, then, is to address 3 specific situations that are quite common in terms of data layout and data storage. First is the idea of where you would have an array of structs. We've seen that in the previous example, so we want to be able to find out ways of addressing that to make it easier. We also want to address the idea of having a struct which contains a struct within it. So storing a collection of data within a collection of data. And then, a very common thing, the idea of having a struct with an array at the end of it. So how do we deal with that? And so these are the 3 things that we want to address with the object layout project. Now, the idea behind object layout is to take the same approach that was taken with the concurrency utilities. If you go way back in terms of Java, and you look at JDK 1 or JDK 1.1, 1.2, writing multi-threaded code was very difficult. Right from the very beginning, you had the thread class. So you could create as many threads as you wanted. You could do things in separate threads. That was easy. But having those threads cooperate when it came to actually sharing data was very difficult, because really you only had 4 methods from the thread class. You had wait, interrupt, sleep, and notify to coordinate the movement of those threads in the data. You could use synchronized blocks, you could use synchronized methods, but very primitive ways of doing interactions between threads. So Doug Lee came along and said, we need a better way of doing that. We need higher level constructs to do that. And so what he did was he wrote a library. the concurrency utilities. But he did it outside of the JDK. So he simply wrote a set of libraries and said, right, what we need are things like atomic operations. We need things like mutexes. We need things like read-write locks, and so on. At that point, that library could be used completely without any problem on any JVM, because it just used Java code to implement those things. When in JDK 5, that got brought into the standard class libraries, suddenly the JVM was able to know about these standard libraries. And so what it could do is it say, right, I recognize that these are part of the standard libraries, and I can do things underneath which will optimize behavior. It will optimize performance for these things. Good example of that is if you look at an atomic long compare and set, you can actually write that using synchronized blocks. So you can do it in Java without any special syntax, without any special libraries. You simply use a set of synchronized blocks, synchronized methods, and you can do an atomic long compare and set. But once that gets into the core libraries, the JVM can look at that and go, hang on, I know how to do that much, much quicker. So we'll use a single x86 instruction to do that compare and set when we see that as part of the standard libraries. What we want to do with object layout is the same thing. So take the idea of writing these libraries as a standard set of libraries which use standard Java, and then move them into the JDK so that the JVM can then intrinsify the operations and actually improve the performance underneath without you having to change anything in your code. Let's look at how this works then. So let's look at the idea of an array of structures. And what we've done is to create the appropriately named class called structured array. Right. Now, a structured array, because it's a collection, is a generic class. So it has a type associated with it, the type of objects that you want to store in there. And what we have here is a collection of object instances of an arbitrary type, but an exact type T. Now, that's very key here. We're talking about an exact type, not types and subtypes, only the type T. And so that is similar to the idea of an array of structs, where you can't change the type of the structure. You can't make the structure bigger, you can't make the structure smaller in terms of the array that you have when you create it in C. So we want the same thing with our structured array. It is arranged like an array. So it has a set of elements in an array, and those have indices. If you want to reference one of those, you can simply call the get method, pass in the index, and it will give you back the element at that point in the array. So same semantics as using an array. The collection is immutable. Now, I mentioned the idea that we're not looking at immutable objects. This collection is immutable. The objects which are stored in it do not necessarily have to be immutable. If you want to put immutable objects in it, fine. But if you want mutable objects, that's fine as well. You can change the values stored in those objects without any problem at all. But the collection itself is immutable. Again, it's the same approach that you have with an array of structures in C. So from an API point of view, you have a get method, but you don't have a put method. You cannot put elements into this array. You can only reference them once they've been created. So how do we create one? Okay, to do that, we need a factory method. We don't use a constructor. I'll come back to that in a moment. We use a factory method. So simplest form is to say, okay, I have a structured array. I want a new instance of that, and I'm going to store some class in it. So I need the class of that class, which I do by saying some class.class. And I need to tell it the size of the array that I'm creating, 100 elements. All of the elements in that array will be constructed at instantiation time. That means that all the objects that are going to be put in that structured array are created when you create the structured array. And because when you create objects, often you want to pass values as parameters to the constructor, to have them constructed in particular ways, there is support for that through this thing called CTOR and args, for constructor and args. And that will allow you to pass arbitrary values to the constructors of the objects as they're created when you create the structured array. And that's done based on its position in the structured array. So let's look at how we do that. Let's assume that we have a very simple class called foo. And foo has a constructor which takes a long value. And what we want to do there is very simply to have the index of that object within our array as the parameter passed to the constructor. So when we want to construct an array of these, what we do is, first of all, we need to retrieve the constructor from our class foo of the appropriate version. So the one that takes a long as a parameter, because we could have multiple constructors. So in this case, we want the one which takes a long, and we get a reference to the constructor of foo. Use reflection to do that. And then when we call our factory method, the new instance again, we still pass in the type, so foo.class. We still pass in the last parameter, which is the number of elements that are going to go into that array, so 8. But now we also have this other thing in the middle. And what this is a constructor and args provider. So this is a functional interface, which means we can use a lambda expression to represent the single abstract method of that functional interface. So in this case, we're saying that what gets passed in is a context. And the context includes the information about which position this object is in terms of the array as they're being created. And so we can then call the constructor and args, we can create a new constructor and args of type foo using the constructor and using the context to retrieve the index of that. So that's the value that will be passed to the constructor in order to construct the objects as we do all of those objects as we create the structured array. So all of them will get their index passed as a parameter to the constructor. Now that's a very simple example. Obviously, if you're trying to do more complex things, then you can use more complex versions of this. But you have the flexibility to be able to construct those objects using specific parameters when you construct them as you construct the structured array. Liveness. Now this was something that was considered a couple of times when it came to understanding how these things would work. And if you think about an array of structures in C, you allocate memory for that, and so long as you are using one of those structures in that array, then you can't free up that memory. So all of the memory for that particular allocation has to be maintained if any of the structures are still being used. So the first idea with structured array was, well, we'll do the same thing. So we'll assume that if you have a reference to any of the objects in that structured array, then we'll keep the whole structured array alive. Even if you don't have a reference to the structured array itself, but you've got an array, you've got a reference from somewhere else to one of those objects, we'll keep everything alive, because that's the same idea as how it works in C. Okay, but if you think about it a bit further, you kind of go, well, that actually doesn't really make a lot of sense, because objects already have liveness, which is tracked by the garbage collector. So the garbage collector underneath is doing all this work to keep a note of which objects still have references to them and which objects are still live. So the JVM does that for us. So it doesn't actually make sense to say that if you have a reference to one object in that structured array from somewhere else, we keep the whole thing alive. Because let's say you've got 10,000 elements in your structured array, you get rid of the structured array reference, but you've still got a pointer from somewhere in your application to one of these elements. You don't want to keep all 10,000 alive just because you've got a reference to one. That would be very inefficient. So a structured array simply becomes just like any other collection. If you get rid of the reference to the collection can be garbage collected. Any objects in that any objects in that collection which don't have references from elsewhere can also be garbage collected. Same thing applies to structured array as it does to any other collection within Java. So all of the collection members are simply plain old Java objects. Nothing different in terms of what you're storing there. So what are the features of a structured array? Well, the first thing is that we realize this is 2016 and that you might actually want to have more than an int size for your array. So we'll actually use a long as an index. So it's kind of reasonably future-proof. Nested arrays are supported. So you can have multi-dimensional structured arrays, you can have composable structured arrays. So you can have a structured array of structured arrays. And then those structured arrays can have elements within them. There's no problem with that. And we'll talk a little bit more about that later on as well. Structured array is subclassable because we see a number of situations where you might want to take a structured array, subclass it, and add some things to it to make it more specific to your type of application. Structured array is not constructible. Have to use a factory method, as we've already seen, in order to create your structured array. So does anybody spot the contradiction there?
How is it subclassable then?
Good. How is it subclassable? If it's not constructible, how can you make it subclassable? There's two things which are actually opposed. Well, there's an answer to that, which is constructor magic. So what happens is that the constructor is available. So there is a public constructor which can be called, because there has to be in order for it to be subclassable. So there is a public constructor that can be called. But the constructor contains or is passed context as to where that constructor is being called from. If the constructor is called from the factory method, the context is right, and so the constructor goes, yep, okay, just carries on and does what it needs to do. If you call the constructor explicitly from outside of a factory method and you try to instantiate it directly from the constructor, you won't have the right context, and so the constructor will go, oh, not being called from factory method, throw an exception so you can't actually create the object. So it's not quite that you can't construct an object, it's just that it will throw an exception when you try to do it. Now what we've done is to optimize this within the JDK, because being as all, we have our own JVM, so we understand how to make changes in the JVM, and we've done that in order to support the idea of structured array. We've introduced, in effect, some new concepts from the point of view of the heap. So this is purely in the JVM, doesn't make any difference to your code. What we have is the idea of contained and container objects. So a structured array is a container object. The objects that are stored inside it are contained objects. That's very logical. What a contained object allows the JVM to do is to find from that what its container is. So it allows you to track back to the parent, if you like, the container of that object. That way, when the garbage collector runs and it looks at objects and says, right, I need to move this object somewhere else in order to do garbage collection, it will see that it is actually a contained object. So rather than moving just that object, it'll say contained object, follow the link to the container, which is our structured array, and then move the container, the structured array, and all of the objects associated with it as a single unit. So that way, because we create all of the objects in our structured array at instantiation time, we can make sure they're contiguous in memory. Then, when we move them as part of garbage collection, we treat them all as a single unit of allocation, and we can then move it together and keep everything contiguous. And that way, when you do striding, when you do iteration over the objects in the structured array, you'll get the advantage of the prefetching. So we've done that with our virtual machine. We've also looked at doing it in the OpenJDK code and figured that it's actually fairly easy to do that. So how do we get the benefits of this? So as I say, because we move everything as a single unit, the prefetching, the striding, comes for free, because we're just accessing memory in a fixed pattern, and the hardware underneath will spot that and start doing the prefetching. We don't have to do anything different in terms of the JVM. Dead reckoning is a little bit different, because we have to remember that unlike in a struct, where all the data is everything that we're dealing with, objects are a bit bigger. So they have an object header, there's other information. So you have to do a little bit more complicated calculation, but we can still, from the information we have, do dead reckoning to find a value rather than having to follow a pointer and do an indirection through that in order to get the value that we actually want. There's a lot more detail about how that actually works in terms of the project discussion on the website. So let's look at the other ideas of object layout, which is having a struct with a struct inside it and a struct with an array at the end of it. Again, let's go back and look at how this works in C. So if I want to create something like a line, I'm going to have a struct which contains two structs, struct within a struct. And each of those structs is a point, and a point in this case will have two values, int x, int y. So same as we've seen before. And in terms of the memory layout, we'll just have four values, contiguous in memory, x, y, x, y. Those will be treated as if they are two endpoints and treated as if they were a single line. So all it is just having those values contiguous in memory. If we look at how Java does that, it gets a bit more complicated because now we've got implicit pointers involved rather than having memory addresses contiguous in memory. So if we create a line, we can do that. We can have a point, which is endpoint1, a point, which is endpoint2. We can instantiate those. But of course, that gets allocated somewhere in the heap. We don't know where. And we have these two references, endpoint1, endpoint2, which we have to follow in order to get those values. Right. So how do we do that? Well, we have to be a little bit more complicated with this. What we do is we have to give the compiler and we have to give the virtual machine a little bit of a hint about how this works. So if we want to create our line, we can have our endpoint 1, but this time, in terms of actually creating it, rather than just calling the constructor, we will use an intrinsic object or intrinsic objects class to create that object for us. So we'll use a factory method, and we're going to say we're going to construct it within this object. So that's effectively what we're trying to do. So it's the principle behind it. It's not actually what happens, but I'll point out how that works in a moment. So to do that, we have to tell it the name of the object, so endpoint 1. We have to give it a reference to the class that's going to contain it, or the object that's going to contain it, so that's this. And we also have to have a lookup, so that's how we can find the constructor, so we can actually construct the object and do it using our factory method. So we use a method handle to do that. Now that's one thing, because we use method handles in this particular part of the system, we are limited to only using Java SE 7 or later. So this won't work in Java SE 6 or earlier. So then, what we do is we make the struct that we have, if you like, contiguous and part of our object. So we can allocate it, and then we can still use our pointers in exactly the same way. So we can still reference endpoint 1, we still reference endpoint 2. It all works exactly the same. There's no difference in terms of the code that we use to reference the pieces of data within our object. One little sort of fly in the ointment here is the fact that you've got to survive reflection, because reflection allows you to do some things which are a bit kind of less than ideal. But assuming that you don't do any nasty things with reflection, there's no problem with this. And so what effectively happens is that we end up with this. So rather than putting the point within the object where we embed it, what we do is we kind of embed it at the end. So we allocate the space for the line object. We also allocate the space for the point objects at the same time, and we make them all contiguous in memory. That way, we can treat the line and both points as if they are a single unit of allocation. And when we do garbage collection, we can move it around doing that. That way, when we want to reference endpoint 1, in your code, you'll simply use the implicit pointer to say, give me a endpoint 1 and then do something with it. But the JVM underneath can go, okay, well, endpoint 1 is the point that's immediately after this object, so it can use dead reckoning to calculate the address of that rather than having to retrieve the address and then follow it to get the pointer and so on. So it's a lot more efficient in terms of the memory, and it allows you to do dead reckoning, allows you to get the same idea as you get with a struct within a struct in C. Struct with an array at the end. So what we can do here is say, okay, we want to put an array at the end. So we'll have arrays of the types that we need. We've created primitive long array, primitive double array, and so on. So we have the ability to have arrays of any primitive type that you have in Java. And then if you want objects within that array, you can use a reference array of a specific type. So you either put primitives in it or you put an object, and then you can simply do that. Structured array, as I say, is also subclassable, so you can put a struct with an array of structs at the end using that. And so the idea is that all of these things are then composable. So we end up with a sort of fractal kind of idea. Start off with our heap, and then within that, we are going to create a structured array which has structured arrays as objects within it. That then has the objects themselves, which are structured arrays of, let's say, type foo, which then contain objects of foo. And then foo itself could be more complicated. So we could have a struct within a struct. So we could intrinsify a bar object and a baz object so that we get this idea of putting the baz and the bar object after the foo object. And then we can even say, okay, let's have an intrinsic array at the end of that, which will be a reference type array of type mu. And we can put all that together. Everything will be treated as a single object. And the whole thing, this structured array of foos, will all be treated as one big object. And it'll be allocated as one big object. It'll be moved around as one big object. So clearly, if you start building big ones, if you've got lots of elements in there, you may find that the allocation system will immediately say, this is a very big object. I'm not going to allocate it directly in the young generation. It'll go straight into the old generation and bypass the idea of going from the young generation to the old generation. From a status point of view, we have code up on GitHub. There's a link from ObjectLayout.org, which you can follow to find the code for this. It is fairly mature semantically. Gil likes to say he's still trying to work out the spelling. So some of the names of these things might change a little bit based on feedback and so on. We've done implementations for Zing. We've done an implementation for OpenJDK. And the kind of numbers that we're getting in terms of performance are looking pretty good. So we have one example where we've taken the hash map and the get on that. We've used a structured array underneath and done some things there. And we get about a 6% improvement in performance on doing a get to a hash map. Now, that might not seem like a, well, okay, 6%, yeah, it's not like huge, but if you're doing millions of operations, 6% could be something that actually gives you a reasonable improvement in performance of your whole application. Having done all this work and got the basic ideas there, what we need to do now is move that into the JDK so that we can get the standard JVM or the Oracle JVM to intrinsify the operations and give you better performance outside of the library code. Obviously, that will require working through things like the JDK enhancement proposals. It will require things like working with the JCP and JSRs. But the good news is that we're already doing that. So Azul have actually achieved a significant milestone, which is we have finally got a JEP through the process of approval. Now, this was a different thing. It was a spin weight hint, which is a very small change, but we actually proved that you can get a JEP through the process without being Oracle. So there is hope there that we can do that. And similarly, we work with the JCP. We're on the JCP EC so that we can get things, hopefully, working with them to do the JSRs. So just to summarize then, the idea here is to create a new set of Java classes that give you the ability to have this concept of a struct array. And even though you don't have to do anything significantly different in terms of code, there's a little bit of things with method handles, a little bit of things with calling the factory method for constructing them, then it will work in exactly the same way. You can use it out of the box, no syntax changes, no changes required to the virtual machine, although obviously to improve performance, then changing the VM will allow you to do that. Relatively simple, relatively isolated. As we've already proved with our sort of proof of concept implementation, it does work. We can make it go faster, so there's benefits there. And I actually find myself in a very unusual position here because I have 5 minutes left, so I can take questions.
Yeah, I've got a question. How do you handle in detail garbage collection when the structured array is destroyed and no longer needed, no longer referenced, but you've got some elements in there which are...
Right, so the question is, if you dispose of all references to your structured array, but you still have some references to the objects in there, in that case, it works in exactly the same way as if you had an array list, for example. So if you have an array list, you've got elements within that. If you stop referencing the array list will be garbage collected. Any elements referenced by that array list, because that ceases to exist, will be garbage collected. But if you've got references from somewhere else to any elements in that array list, those will still be kept as objects in the heap. So it works in exactly the same way as an array list.
But are those really objects? Isn't this
No, because all it is contiguous. So you've got your structured array as one object, and then all the objects that are in that structured array are just contiguous in memory. So we're not actually creating a new type of object which has all those objects inside it. It's just putting them contiguous in memory so we can get the advantages of dead reckoning and striding.
So then after destroying the collection, you can just move around?
Yes. Yes, absolutely.
Why only 6%? Iterating over an array in C, two-dimensional array.
Yeah.
If you switched in X and Y, did it in wrong order, you had cache misses all the time, and it was like order of magnitude slower than it should have been.
Yeah. Yeah, so that was a hash map get. It wasn't iterating over an array. So that's a little bit different. So it's not quite a like-for-like comparison. I don't know of the numbers. I haven't looked to see whether we've done any numbers to say, okay, well, if we take an array of these and we actually iterate over them, how does that compare to iterating over an array of structs in C? That would be an interesting comparison. We should do that. Yes.
Numbers could look much better.
Yeah. Yeah, you're right. We should definitely do that.
Do you have any publicly available benchmarks for the JDKs, the sync JDK and the hotspot JDK?
Yeah, if you look on the ObjectLayout.org website, anything that we've got that we've done in terms of benchmarking is on there. So we're not hiding anything. Everything that we do is published on the website.
And is there any performance gain from using ObjectLayout on the hotspot JVM?
No, because they don't, at the moment, they don't intrinsify the operations. As I say, what we've done is we've taken the OpenJDK code because we do our own build of that Zulu, and we've actually made the changes. So from the point of view of taking hotspot and modifying it, it will work. But obviously Oracle would then have to kind of buy into that and take those into their VM.
Do you think that ObjectLayout could be re-implemented after Java 9 comes out with the pointer mechanics? And so that maybe ObjectLayout could work and give performance gains without actually modifying the garbage collector?
Difficult question to answer. I don't know. I'm going to say that. My first thought is probably not, but then I'm bound to be proved wrong. So I'll go with I don't know.
Okay. Do you have any drawbacks, like those huge objects? Is it a drawback that they take much memory and then the rest
No, I mean,
goes?
yeah. So are there any drawbacks? I guess the only thing is it's a little more involved in terms of the coding. So if you need to use constructors and you want to pass specific parameters to a constructor as you're constructing the objects in your array, that's a bit more fiddly than just creating an array of objects as you would do now. So it's a little bit more fiddly. So, I mean, that's one kind of minor downside. But
what about the rest of the objects that go behind this, for example, our huge...
Yes. So, I mean, in terms of storage, it doesn't actually, no, it doesn't require any more storage because you've still got a collection. So you've got a structured array, which again, you can kind of treat like an array list or a hash map or whatever.
No, I'm talking like, for example, we constructed our big array object, and then we have some other objects that end up on the end of our memory.
Mm-hmm.
And then if we switch between accessing them, then we have fast access to this object, but then slow access to other objects.
Yeah, no, I don't think that would actually, because you're still going to have the same reference that you would have before. So if you kind of just took it all away, it would still be the same speed of reference for those objects at the end of it. So I don't think so, no. Okay, one more question.
In C, you are able to calculate the expected size of the structured array, right? And are you able to, I don't know, it might be tricky in Java to predict the structured array, the size of the structure, the continuous side, continuous.
Oh, no. We absolutely can predict that because we know we have to create all the objects at instantiation time. So we know exactly how big those objects are. So we know exactly how big the structured array is. So there's no element of doubt in there.
And ObjectLayout can return the size of it.
Yes. Yeah, absolutely. Yeah. Okay, thank you very much.